Hi, my name is Oktay. Welcome to today's video about basic principles in organic chemistry. That's hybrid orbitals and Hückel's rule. This is a picture at the left of the molecule methane, CH4. 60 to 90% of natural gas is methane. To the right, you can see the structure of this molecule. That's a tetrahedron structure with an angle of 109.5 degrees. And you can see all the bonds have equal length. However, electron configuration of the carbon is 1s2, 2s2, 2p2. So carbon has in the outer shell two different kinds of orbitals. The s orbital is spherical, and the p orbital has a dumbbell shape. How can you make 4 equal bonds with different types of atomic orbitals? This is a picture of the shapes of the s and the p orbitals. The lowest energy orbital is the 1s orbital, then the 2s orbital, both are spherical, and the dumbbell-shaped p orbitals, px, py, pz. This is the solution. You create hybrid orbital. The single 2s orbital merges with the 3 p orbitals, and you get this structure. That's the sp3 hybrid orbital. Now you can have 4 equal bonds with equal length. Since the hybrid orbital is made of just 1 s and 3 p orbitals, there's 25% s orbital structure and 75% p. And this orbital allows you to have a bond angle of 109.5 degrees. That's the tetrahedron bond angle. This is another simple molecule, that's ethylene, C2H4. It has a planar structure. You can see the angle is about 120 degrees. And it contains a CC double bond. There are 2 bonds. The bond that is in the connection line of the 2 nuclei, that's called the sigma bond. And the bond that's beyond the connection line of the 2 nuclei, that's called the pi bond. The CC double bond has an average bond energy of 614 kilojoule per mole. And the CC single bond with just 1 sigma bond has a bond energy of 347 kilojoule per mole. So the difference is the bond energy of the pi bond, which is just 267 kilojoule per mole. So the pi bond has a lower bond energy than the sigma bond. And that's the basis of polymer chemistry. For example, that allows you to polymerize this molecule ethylene to polyethylene. And that's an exothermic reaction because pi bonds are converted into sigma bonds. And you need cooling to control this reaction. This is how the sp2 hybrid orbital is shaped in ethylene. It has a bit higher s percentage than the sp3 orbital, and it is not as stretched as the sp3 orbital. It is 33% s, 67% p. And this means there's a pz orbital that is not used for hybridization. That's the orbital that makes the pi bond. And this sp2 hybrid orbitals have a bond angle of 120 degrees. This is so-called HOMO of the ethylene molecule. That's the highest occupied molecular orbital of ethylene. That's this pi bond. And this is the sigma bond. This is another simple molecule, acetylene, C2H2. It has a linear structure, and it contains sp orbitals. The sp orbitals are made of 1 s orbital and 1 p orbital. They have 50% of each orbital. And the remaining 2 p orbitals make the 2 pi bonds. The bond length of the triple bond is smaller than that of the double bond, and that's smaller than that of the single bond. The bond angle is 180 degrees. This is a nice picture. It shows you the electron density in acetylene. The pi electrons that are beyond the connection line of the nuclei are distributed symmetrically. There is an even distribution of the pi electron. This is a molecule butadiene, C4H6. It has also a planar structure, also sp2 hybridized. Each carbon has a p orbital, and in this case, all the 4 p orbitals can overlap. And this is called a conjugated pi electron system, which is alternating double and single bonds. The pi electrons can move freely in this big pi orbital. That's called delocalization, and this effect is called mesomeric effect. Open structures like butadiene have a low mesomeric energy. This is another example, benzene C6H6 at top. It's Hückel structures. Scientist August Hückel spent several years of his life finding out this structure. And he recognized this resonance structure, electron delocalization. At the top right, that's the planar hexagon structure with the 120 degrees angle, bond angle. Bottom left, these are the sp2 hybrid orbitals that overlap and make the sigma bonds. They are restricted to their molecular orbitals. Here you can see the 6 p orbitals. They can overlap and make this delocalized pi electron system, and the 6 pi electrons can move freely inside this ring. That's the simplified structure of the benzene molecule, which also shows the delocalized pi electron ring. And benzene is known for its high mesomeric energy of 151 kilojoule per mole. This means you get a stabilizing effect by making this ring of 151 kilojoule per mole. This compound is called aromatic compound, and it tends to substitution reactions, not addition reactions. This is a way to check in an experiment if this theory is really correct by measuring the bond length. Ethane has a bond length 153 picometers, acetylene 134 about picometers, and benzene is in the middle with 139 picometers, and that's what we expect, because these bonds are basically 1.5 bonds, because the pi electrons are delocalized. These are the molecular orbitals of benzene. The highest occupied molecular orbital is called HOMO, and the lowest unoccupied molecular orbital is called LUMO. And the energy difference between these two molecular orbitals is important for the properties of these compounds. That's Hückel's rule. Erich Hückel was a German physicist and chemist. This is the rule: planar cyclic conjugated pi electron systems with 4n plus 2 pi electrons are aromatic. All rings in the atoms must have p orbitals. And the systems with just 4n pi electrons are called anti-aromatic. At the left, there are a few examples. Top left, that's benzene. In this case, n is 1, that's aromatic. Naphthalene, n equals 2, is also aromatic. And anthracene is n3, is also aromatic. Bottom left, the cyclopropanium cation with n equals 0 is also aromatic. Perilene 2. But this compound, cyclooctatetraene, is not aromatic, neither anti-aromatic, but non-aromatic because it is not flat. It is more shaped like a bathtub. This is an example of an anti-aromatic compound, a very unstable compound, that's cyclobutadiene, C4H4. In the middle, that's the molecular structure. And this molecule can be detected at very low temperatures, but it's very unstable. However, there's a trick to stabilize the structure. and that's at the right. That's this derivative. 1, 2, 3, 4 tetrakis T-butyl cyclobutadiene. Now, this molecule is more stable because the steric bulky functional groups, the T-butyl groups, prevent the reaction of this ring. Here's another example, Cyclopentadiene, C5H6. In this case, you have a CH2 group, that's called a methylene group. This is not non-aromatic because this carbon is not sp2 hybridized, it's sp3 hybridized, and it has no p orbital. However, we can now predict one of the properties of this compound, and that's it's acidic. Because when it's after it loses one proton, you get here a free electron pair. Now you have a 6-pi electron structure, and that's aromatic. That's why this cyclopentadienyl anion C5H5- is aromatic. The ring atoms don't have to be carbon, they can be other atoms. And these kinds of compounds are called heterocycles. Here are a few examples. That's furan with oxygen in the ring, thiophene with sulfur in the ring, pyrrole with NH group in the ring. In these two cases, one of the two electron pairs is part of the pi electron system, the other is not. Pyrrole and the electron pair is part of the electron system. Then you have pyridine and pyrimidine, and in this both cases, the free electron pairs are not part of the pi electron system. All these molecules are 6-pi electron systems, and they are aromatic compounds. And nature makes use of these molecules. Here's one example, that's the molecule DNA, Deoxyribonucleic acid. That's a molecule of life. It has 3 components. That's deoxyribose and phosphate. They make the backbone of this molecule. And you have the 4 nucleobases, adenine, thymine, guanine, cytosine. They are in 2 pairs. You can see here the dotted lines. They are very important for the structure of this molecule. These are the intermolecular hydrogen bonds. They are not as strong as atomic bonds, but they're strong enough to give this molecule its 3D structure, and they can be opened, and this allows this molecule to be replicated. That's why it's a molecule of life. So you have 4 letters, A, T, C, and G. And in nature there are 21 amino acids, so you need a triplet of nucleobases to code 1 amino acid, for example GCT, guanine, cytosine, thymine. This is the code for the amino acid L-alanine. And this is a beautiful flower table of the genetic code. Here you can see the correlation of the 4 nucleobases and amino acids. For example, glycine has the code GGT or GGC. For alanine, GCG. Methionine, ATG. And there's also a code for stop. When the protein is finished, then the production stops and you get the protein molecule. This is a picture of a Ouroboros. This is an ancient symbol from Egypt from the 14th century before Christ. It represents the beginning and end of time. And this Ouroboros was the inspiration for Auguste Kekulé's structure of benzene. And this is a bronze statue of Auguste Kekulé. It is located at the Altes Chemisches Institut in Bonn, and that's in Western Germany. That was today's video about basic principles of organic chemistry, the hybrid orbitals, and the Hückel's rule. Thank you for watching. Have a nice day. Bye-bye.